So you can't think about water and hydrogen bonds without thinking about acids and bases. So we're going to go over some basic properties, and this should probably be a basic review of some of the things you've learned from general chemistry. So first of all, when we're talking about acids, right? So acids are typically things that are molecules that behave as a proton donor, right? So they give up an H plus. And then these are also known as what we call Bronsted acids. And then when you think about bases, bases are things that are typically proton acceptors. A common proton acceptor might be something like an OH minus. And these are the very common sort of things that we think about when we're thinking about acids and bases. Okay, so when we think about acids, we think about acid strength. And when we think about acid strength, we really want to think about the acid's ability to dissociate a hydrogen ion, and also think about conjugate bases. But let's first think about an acid. So a basic structure of an acid would be known as an HA, right? A being the conjugate base. So the base would be something that would, again, be attracted to the hydrogen ion. And so this would be the conjugate base. So every single acid can break down and form both the proton with its conjugate base. Right? So this is the very most simplest definition of what happens to acid and how it dissociates into water. So then you have this other feature here called Ka. And so this Ka constant value is really looking at the dissociation and looking at the multiplication of the products and its concentrations over the concentration of the reactant, in this case the acid. So this is nothing that should be unfamiliar to you because you looked at equilibrium constants and constants before. And so this is what happens when you have an acid that dissociates in water. So one key feature is that the greater the value of the Ka means you have a very strong acid. Okay, and so the correct form of the equation when thinking about what happens with an acid in, say, water in this case, okay, would be that the acid dissociates, but in fact the correct version of this is to say that you have a hydronium ion, right? So this is the conjugate acid to water because the water's taken up a hydrogen, and then you have your conjugate base, which is now your A minus. And this is no different than the A minus that you saw before. But this complete reaction and this complete thing that you see right here represents the correct form of the equation of what happens when a strong acid dissociates in water. In this case, water can act as a base. Another thing to think about is, again, the ionization of the water. So here's a better description of that Ka value. And in this case, we're looking at water, right? And Ka is the, again, dissociation of water going to its two parts, in this case H plus and OH minus. And so it is a combination, again, of the multiplication of the products over the reactants. So again, we're just expanding the original formula that we talked about in the previous slide. The other key feature to think about when thinking about pure water is that the concentration of pure water is 55.5 molar. This is just a value that you just have to remember. And so what we can do is we can take that 55.5 and we can put it into the denominator of that same formula we just talked about up here. Okay, so if we do that, this will simplify the equation. And if we just solve for Ka times 0.55, so we move this over and back up, we get the product constant of the concentration of your H plus and OH minus equal to the Kw for water. And another way to look at this as is a representation shown here by showing the complete molecule of water here and how it dissociates into the base and then your proton. Alright, so why does this all make a big difference? Well, when we look at the ion product constant of water, this is measuring the tendency of water to dissociate and give up our H plus and our OH minus ions. And so if we think about this in terms of what happens with pure water, At 25 degrees Celsius in pure water, H plus equals 10 to the minus 7 molar. Okay? And because it's an equal dissociation, this also equals the concentration of your base, or your OH minus. So if we look at the product constant of Kw, which we know was H plus times OH minus from the previous derivation, we now know the two concentrations, they're equal. When we multiply those two, we get 10. We now get the value 1 times 10 to the minus 14. And now, one of the most important calculations that we have for pH is this relationship here, which says pH is equal to the minus of the log base 10 of the concentration of H plus in a solution. And the significance of this is because we're using base 10. And I know a lot of people get base 10 kind of mixed up, but it's really important to understand this because the difference of one single pH unit implies what we call a tenfold difference in the concentration of H plus. So say going from a pH of 2 to a pH of 3 means that with a pH of 2 that there's 10 times more H plus compared to a pH of 3. Another sort of real world example of that is to think about the Richter scale and earthquakes. So if you're in a earthquake Richter scale 5 on the magnitude of an earthquake versus a magnitude of a 6, it makes a huge difference in thinking about the magnitude. So it's a tenfold difference. And that's the same thing that we had to think about when thinking about pH. So going from one pH unit to another really implies a huge fold difference. It is a tenfold difference. And always remember that when we're thinking about neutral solutions, right, we have a pH of 7. One important thing also to remember is that when you have an acidic solution, it's anything that is a pH less than 7, and a basic solution is anything from greater than a pH of 7, so greater than a neutral value. And remember that the complete pH scale goes from 0 all the way up to 14. And I should say 0.1 to be correct, all the way up to 14. Another feature to also think about is when you think about the pKa. This is a constant value, but it really is a measure of the acid strength. So one common way in which we interpret that is to say that the pKa is equal to the minus log base 10 of Ka. So the smaller the value of the pKa, the stronger the acid. And you can kind of think about these in terms of the dissociation constant. But I always think of pH, so the lower scale, less than 7 is acidic. So remember that. And anything that's greater than 7 or greater than neutral is considered basic. And so when you think about the concentration of H+, the smaller the value of the pH, the stronger the acid. Okay, so those two are inversely related. So a low number means a high concentration of H+. So let's go through two examples. If we think about what happens when we have a strong acid, or in this case, a strong base. Okay, so these are two really great examples. So remember that in pure water, H plus is equal to 1 times 10 to the minus 7th molar, which means it's neutral, or pH of 7. So if we're thinking about 1 times 10 to the minus 3, we can almost, if you're really comfortable with pH, think about that in our head. So if we know that 1 times 10 to the minus 7th was a pH of 7, we can say that the pH of a 1 times 10 to the minus 3 molar HCl, or hydrochloric acid solution, means we have a pH of 3. And then we might be a little bit confused by this particular question, because when we think about sodium hydroxide, we should instantly realize, oh, this is a base. So how can we figure out the pH when we're really looking at a strong basic solution? Well, if it's a basic solution, we should instantly know that the pH value, or sort of back of an envelope guess, is that it will be some value above 7, right? Because it has to be basic. So if we look at and think about the pOH for this situation, the pOH would actually be a value that is equal to 4, right? So that's not the pH. So in order to figure out the pH, we'd have to say 14 minus 4. because remember the pH scale goes all the way up from 0.0.1 all the way up to 14. So the pH would be 14 minus 4, which is equal to 10. And this value for a 1 times 10 to the minus 4 molar sodium hydroxide, pH 10, does make sense. Okay. And so we can actually do this with the detailed calculations. So if we're looking at the same problem for 1 times 10 to the minus 3 molar HCl, the hydronium or correct concentration of our H plus of the cell dissociation of this strong acid in water is a value of 1 times 10 to the 3 minus 1 times 10 to the minus 3 molar, excuse me. And so the pH is equal to the log, right, minus the log of the concentration of H plus, which in this case is 1 times 10 to the minus 3. So if you're feeling a little uneasy, right, you can go to your calculator, type in 1 times 10 to the minus 3, 1 e to the minus 3, and then push the log button. And then always remember, right, there is this negative sign at the front. So you'd get some value that is the log of 10 times minus 3 equal to minus 3, but because there is a negative sign in front of the equation, right, you'd get a value of 3. All right. And then the second question was related to what is the pH of 1 times 10 to the minus 4 molar sodium hydroxide. So given that the OH minus concentration is 1 times 10 to the minus 4, we know, again, this relationship between the OH minus and the H plus or hydronium means that it's equal to 1 times 10 to the minus 14. So if that is the case, then our proton concentration must be 1 times 10 to the minus 14. If we figure out hydronium, that would be 1 times 10 to the minus 10 in this calculation. And then we can figure out the pH. So again, we plug it into the pH equals minus log of 1 times 10 to the minus 10, and we'd end up with a calculated value of 10. So these should be pretty straightforward acid-base problems for you because they're both a strong acid and a strong base calculation. Again, things that you would have seen in your basic general chemistry course. The part that becomes really interesting is with the Henderson-Hasselbalch equation. So I'm going to go straight to it. This is the formula for the Henderson-Hasselbalch equation. And it is determining the pH by knowing what the pKa of an acid is and thinking about what happens to the dissociation of that acid in a solution. Okay? And the reason why this is important is because in biochemistry and in most biological systems, we're not looking at a strong acid and a strong base, but we're looking at a weaker acid or something that might be buffered. So a situation that's biochemically relevant requires the use of the Henderson-Hasselbalch equation. And so you can look at this derivation, but I'm going to just cut to the chase and say that this is the way in which you'd figure out and determine the pH of a situation where you have probably a weaker acid, right? Not a strong acid that's in the pH range of 1 to 3 or so, but maybe something that goes from 5 to a little bit closer to 7, which is something that you'd see in a biological system, okay? So why is this important? So the Henderson-Hasselbalch equation is the pH equal to the pKa plus the log of the concentration of A minus over the concentration of HA, right, as we saw previously. But where it becomes as important is when we think about the pKa values of these weak acids, as I mentioned before, okay, and its conjugate base. So the pH of the solution equals the pKa of the weak acid, all right? And so in a biochemical system, this is what happens when you look at the enzyme activity. So we haven't quite talked about enzymes yet, but enzymes are things that catalyze reactions. And here are examples of 3 different enzymes: pepsin, trypsin, and lysozyme. And I'll let you know that these are things that chew up things, especially in the gut or in the stomach. Okay, so in order to process proteins and enzymes, we need to use other enzymes to break them down. And so in your stomach, you know that it is very acidic environment. So if we look at these three graphs here, pepsin, trypsin, and lysozyme are three different enzymes that have different activity peaks at different pHs. So you don't want everything reacting at a pH of 7. You don't want everything reacting at a pH that's very basic. You want it to vary depending on the situation and the location of an enzyme. So in this case, you can see that pepsin is most active right up here, right? At roughly, if we look at the pH, of a pH of a little bit more than 2. So it works most efficiently and actively at a pH that's very low, or a pH of 2. And then we come over here to trypsin, and we see that the peak activity, enzyme activity, is up here. So if we, again, we look at where that is on the pH scale, that's a little bit more on going up in the scale. So it's still acidic, but close, a little bit closer to neutral. Okay. And likewise, we look at lysozyme here that also has a peak activity, right around a pH of 5. So this is just showing you that different enzymes may have a similar function, but they are very distinct from one another because they can digest and cut apart proteins and break them down at various different pHs. And that's because each one of these enzymes have a different, what we call pKa value. And we're going to get to a little bit more of this detail when we start talking about amino acids in the next chapter. So stay tuned.